When we work with solutions, we often express their concentration in terms of molarity. The symbol for molarity is the capital M, and its formula, or the way that we calculate it, is moles of solute, MOL is our abbreviation for moles, divided by liters of solution. It brings up the whole question of what is a mole? And like I said, mole is abbreviated MOL, mole. What is a mole? A mole is equal to 6.02 times 10 to the 23rd particles of substance, or pieces of anything. 6.02 times 10 to the 23rd particles of a substance. This is a very, very large number. If we were to look at it and take it out of its scientific notation, it gets very long and cumbersome. Because as we move the decimal point to the right, we have to keep adding in all of these zeros. We have to move that decimal point 23 times. Because it's 10, it's being multiplied by 10 23 times. So I've moved to point 1, 2, 3, 4, 5, 8, 11, 14, 17, 20 times. 3 more times. So there is 6.02 times 10 to the 23rd without its scientific notation. It's a huge number, and it's very hard to conceptualize. What is a mole? A mole is this many atoms, this many molecules, this many particles of a substance. Did a little experiment with students. They were working in teams and they were counting, and they could count, well, they were counting back and forth. They were getting about 120 counts. In other words, they could count to 120 in a minute. I started thinking about this, working with this a little bit, thinking about, well, how long would it take to count to Avogadro's number? That's the name of this number, 6.02 times 10 to the 23rd. How long would it take you to count that high? Well, if we take this number, 6.02 times 10 to the 23rd, and we divide that by the 120 counts per minute, and maybe you could count faster than that, I don't know, but we're just going to work with this number. It would take you 5.02 times 10 to the 21st power minutes to be able to count to Avogadro's number, the number we use to indicate that there's a mole. That's a long time, but really, how long is that? We take that number, 5.02 times 10 to the 21st power, and divide by 60. We'll know how many hours, because there's 60 minutes per hour. So 60 minutes in an hour. Performing this math will tell us how many hours it would take. 8.36 times 10 to the 19th hours. That's how long it would take to count to this Avogadro's number, the number of particles that there are in a mole. If you were counting at this pace of 120 per minute, day in and day out without stopping. Days. How many days would this be? If we take 8.36 times 10 to the 19th hours, divide that by 24 hours in a day, we find out that that would take 3.48 times 10 to the 18th days. So let's figure out how many years it would be if we took the 3.48 times 10 to the 18th days and said 365.25 days in a year, allowing for leap years. What we find is that at this rate of counting, it would take 9.54 times 10 to the 15th years to count this high. Science tells us, and I just checked on Wikipedia, and so the current number we hold out for the age of the universe, 13.8 billion years. That's 13.8 times 10 to the 9th years for the age of the universe. And that's a huge number also. But if we take 9.54 times 10 to the 15th years, divided by the 13.8 times 10 to the 9th years there are in the age of the universe, what we come up with is finally a number we can start to get a sense of what it means, 691,168 ages of the universe. Well, we can conceive of what $691,000 is and what we might be able to do with that amount of money. But what this is telling us is that if at the beginning of the universe we had been around and we had started to count, and we had counted without stopping to eat or sleep or vacation or anything like that, and today the universe ended, and tomorrow a new universe started, and we were a part of it, and we picked up counting where we left off, and we counted for another 13.8 billion years, and that universe ended, and a new universe started, and we picked up where we had left off, and we counted for another 13.8 billion years. We did this over and over again. We would have to do that through 691,168 ages of the universe in order to be able to count to this number, Avogadro's number, 6.02 times 10 to the 23rd. And that's how many particles, atoms, molecules, there are in a mole of a substance. The number, the quantity of them that there are in a mole. What does that mean? It means, for one thing, atoms and molecules are really, really small. Because if we talk about 1 mole of H2O, liquid water, H2O liquid, we can calculate using the periodic table what the volume of that would be, along with density. We need to use density also. But look, if you look hydrogen up on the periodic table, you'll see it has an atomic mass of 1.01. There are 2 of them in the water molecule because the water molecule is H2O. Multiply by 2, get 2.02. And oxygen has an atomic mass of 16.0. There's only 1 of those in the water molecule, so we just multiply by 1, get 18.02. What this tells us is that 1 mole would have a mass of 18.02 grams. 18.02 grams of H2O. We want to find the volume, we use the density of water. And 1 gram of water has the volume of 1 milliliter. Grams cancels. So it's 18.02 milliliters of H2O. 18.02 milliliters is approximately 3 teaspoons of water. And I would say that's approximately, depending on who you are, 1 swallow. Take 1 swallow of water and you will have taken in a mole, 6.02 times 10 to the 23rd, water molecules. The water molecule, composed of 3 atoms, 2 hydrogen, 1 oxygen, means that if you take a swallow of water, you take in 3 moles worth of atoms. 3 times 3, it's this huge number, times 3. So that's how small water molecules are. You could hold 18 milliliters of water in the palm of your hand. And if you had a small tweezers with which you could pick up a single water molecule and pull it out and set it aside, if you were to do that, and if you were to do that at a rate of 120 water molecules per minute, it would take you a really long time. How long would it take you if you could do 120 of them a minute? It would take you 9.54 times 10 to the 15th years. And if you would start at the beginning of the age of the universe and go to the current time, and then have another universe start again in which you could keep doing it, that would take you almost 700,000, 691,000 ages of the universe. Mole is a lot. It's a lot of particles. The particles are really, really small.